Hey everyone, today I want to discuss about an important specification of an oscilloscope called bandwidth. This will be a short video where I will go through some definitions and the practical measurements of the oscilloscope bandwidth. So what is oscilloscope bandwidth? In short, it is a parameter of an oscilloscope which it can accurately display a range of frequencies. It's stated on megahertz, gigahertz like 100 megahertz, 1 gigahertz and so on. Higher the bandwidth, more expensive the equipment it becomes because it determines the highest and the lowest frequency signals that can be measured without significant distortion or the attenuation. Oscilloscope can measure from DC or 0 Hz signals, so we are interested on the highest frequency signal here. Let's see how bandwidth is defined in a graph. This is the plot between frequency and the gain or voltage. As frequency of the signal increases, the attenuation also increases. The -3 dB loss, or when the voltage is 70.7% of the actual value, the frequency Fc is called bandwidth. It is not that oscilloscope is not usable above this point, but the amplitude of the signal measured above this frequency is greatly attenuated. Typically, it is advised that the oscilloscope bandwidth should be at least 5 times greater than the input signal frequency. For an example, if you are measuring a 1 MHz signal, the oscilloscope should have minimum bandwidth of 5 MHz. Well, that is theory. Let's see how can we measure it in our lab. There are two ways to measure, direct and indirect method. In direct method, it is fairly easy. Let's say you have an oscilloscope, a signal generator, and both are connected by a flat response cable. Assuming this cable has a very low loss and uniform loss across measured signal, we can take the ratio of generator voltage and the measured voltage. And the gain is calculated using this formula. So we keep increasing the frequency of the generator till measured voltage is 70.7% of actual voltage. This is the bandwidth of your oscilloscope. As said, this is assuming the flat response of generator and cables used during the test. Now in indirect method, we use rise time measurement to determine the bandwidth of oscilloscope. The bandwidth can be approximated by the formula 0.35 divided by rise time. This formula is based on approximation of Gaussian frequency response and is valid when the oscilloscope has single pole response. We can use measured rise time directly to calculate the bandwidth, but if the rise time of the generator is close to the rise time of the oscilloscope, then we need to use RMS sum of the actual rise time of oscilloscope, probes and cables, etc. Well, that is the theory. Now let's go to the bench and measure the bandwidth of the scopes that we have here. For direct method, we are going to use signal generator Gigatronix 900. I connected the signal generator to my oscilloscope, and as I sweep the frequencies, the displayed amplitude is decreasing as frequency is increasing. This is due to the effect of oscilloscope bandwidth. Now I am manually increasing the signal frequency from 100 MHz and try to find the 70.7% of the peak voltage to find the oscilloscope bandwidth. The initial peak to peak voltage is around 650 millivolt. The 70.7% of 650 millivolt is around 459.5 millivolt. As I increase the frequency gradually, I see the voltage drops to 459 millivolt at around 620 megahertz of signal frequency. So indeed the bandwidth of this oscilloscope is 600 megahertz. As we discussed earlier, oscilloscope is still usable above its bandwidth, but signal amplitude is greatly reduced. Now let's use indirect method to test the oscilloscope bandwidth. Here I got a very high speed rise time generator from Leo Bondar. It can generate signal with rise time less than 40 picosecond as shown in its test report, which is equivalent to the bandwidth of more than 8 GHz, actually 8.75 GHz. I connected this fast rise time generator to my oscilloscope. As you can see, my scope is measuring rise time of 608 picosecond and lowest I see it around 587 picosecond. If you use the formula 0.35 divided by rise time, it gives the bandwidth of 596 megahertz, which is close to the specification of this oscilloscope. Let's experiment with the bandwidth limit function of the oscilloscope. I have same high-speed rise time generator connected to the scope and measuring the signal rise time. When I enable the 20 MHz bandwidth limit, the measured rise time is increased to around 17 nanosecond. And if you use the same formula, then it translates to the bandwidth of 20.5 MHz. Now let's try on my another high-speed oscilloscope, which has bandwidth of 1.5 GHz. As you can see, the average rise time of this signal is 222 picosecond, which translates to 1.57 GHz of bandwidth, and it matches to the oscilloscope's bandwidth. Finally, let's have more fun with this high-speed rise time generator. We don't know the rise time of this fast pulse generator, right? Well, I got an oscilloscope with bandwidth of more than 20 GHz, and as you can see, I connected the fast pulse generator to my oscilloscope, and it is measuring the rise time of around 36 to 37 picosecond. And if you use the formula 0.35 divided by rise time, it gives the oscilloscope bandwidth of more than 10 GHz. And obviously the oscilloscope bandwidth is higher than the rise time generator bandwidth, so it is measuring the actual rise time of the fast pulse generator. Well, we'll do more fun stuff with this sampling oscilloscope in the future, so keep in touch. Please like and subscribe if you like the video. That's all for today.